Thanks everybody for coming, and thanks Oz for having me. In 20 seconds, here's why business needs prediction. Prediction requires machine learning, and machine learning depends on data. Putting that in reverse, we have data, we give it to machine learning, and it generates models that predict. And those predictions improve all the main things we do as organizations, which is why we also refer to these kinds of predictive enterprise use cases of machine learning as predictive analytics or predictive AI. And that way, we boost sales, cut costs, combat risk, prevent fraud, fortify healthcare, streamline logistics, conquer spam, and win elections. As Morgan Vater of Unilever put it in the foreword to my book, The AI Playbook, machine learning's practical deployment represents the forefront of human progress, improving operations with science. Thank you very much, and have a great rest of the... Actually, hold on a second. We're trying to make these models that I show as golden eggs to deploy. So that core method, predictive modeling, machine learning methods, learns from that data to generate these models that then are meant to run operations better across industry sectors, across enterprise functions. That last step of actually getting it deployed is actually the main point of failure. Most new machine learning projects fail to deploy. They generate potential value by way of generating that model, but fail to capture the value because they don't make a difference. They don't get put into the field. They don't change operations. That's going to be the main thing I talk about today. How do we remedy that? What's the missing ingredients to get these things deployed? Now, there are plenty of positive case studies out there. Even a minority of many projects is a good number of successes. So for example, UPS improves their deliveries of tomorrow's packages by predicting them. So at each of 1,000 shipping centers across the US, they have this optimization problem of assigning tomorrow's deliveries, these packages, to the individual delivery trucks. The problem is, so that each truck has a route that's relatively optimal. Right? So they're trying to decrease the amount of hours the trucks are out and the amount of miles they need to drive. So the problem is that when they have to start assigning these trucks, making the plan, and then actually loading the trucks, they have to start in late afternoon or early evening for on-time departure tomorrow morning, but they have limited information. They have an information gap, which is that some of the packages that will be delivered tomorrow, they don't know about, or at least not for sure, because they haven't arrived at the shipping center yet. So there's this uncertainty problem. So what they do is they augment the known packages that they have in hand with tentatively presumed predicted deliveries based on histories of deliveries, where there's gonna need to be deliveries tomorrow. And now with that more complete, albeit imperfect, view of tomorrow's deliveries, they can do a much better job. This is called package flow technology, and in combination with another system called Orion, which at this point actually introduced prescribed driving directions, so basically GPS. These two systems, which means that not only can the truck have a relatively optimal route, it'll actually drive that optimal route because the driver will be told exactly where to go. These two things contribute to this day to UPS enjoying an annual savings of 185 million miles of driving, $350 million, and 185,000 metric tons of emissions. So a resounding success. But the implementation, the deployment of this project was not clockwork, right? There were a lot of trials and tribulations, a lot of drama, ups and downs. They had to convince executives above them to make this change to large-scale operations based on predictions. Predictions are probabilities. So that idea of acting on probabilities, of embracing probabilities, that really ends up being central to the challenge of deployment. So I'm going to come back to that. And they had to get the loading dock workers to comply and change their behavior. Now, my focus is going to be on the challenge of getting these deployed, but let's talk for a moment to put in comparison generative AI, which arguably is much easier to use than predictive AI. By definition, any of you can just open your phone right now and start using ChatGPT or any of its competitors because you interact with it in English or many human languages, right? So it's so easy to use. It's there. You can try it out. You can ask it questions. You can have it draft marketing. And in fact, quite valuable in that effect. For example, you're starting to see measured performance improvements by using generative AI, such as large language models. Ally Financial is a bank, and they improved their content creation for marketing content by a third. So a 33% improvement in effectiveness. So these are the kinds of things you see, sometimes 50%, 60%. We often, depending on the use case, we often see around 33%. A really unique new value proposition. But even if generative is easier to use, if we want to compare the two, you could arguably say that, in fact, it's harder to use well than predictive AI in the sense of delivering concrete, proven, measured enterprise value. And part of the problem is that it's a bit oversold. There's a little bit of a expectation management issue, that is to say hype. And I think that the central question here is how autonomous can it be? What sort of human level capabilities in general is it set to achieve? How much can you kind of unleash it on the world and let it run autonomously? I'm actually quite concerned about the hype, and I've been writing articles for a few years about the hype. And by the way, I'm going to provide a PDF of my slides that includes notes for many of the slides like this one that have the links. So you'll get that with the extra notes, so you don't have to write down anything if you want to check my additional content. In a nutshell, the story that we're told is that this thing is going to basically be customer facing. So whether it's a chatbot that's helping the end user or consumer, or creating personalized content for marketing to reach out to the consumer, or images, whatever the application is, this story of autonomy, where it's 100% autonomous, right? The problem is that maybe, let's say, 5% of the time, it provides content that's wrong or otherwise problematic. So how do you resolve this story of autonomy with this sort of lack of reliability? So predictive and generative are totally apples and oranges. Generative is getting all of the spotlight these days. It's a little bit of an exaggeration, but the majority of the spotlight. Predictive's value proposition, which has been around for decades, it's older but not old school. Most of its value is still largely untapped. But they solve very different problems. So let me put it this way, if I were going to compare the two. With all the energy and focus on generative, that is sucking the oxygen out of the room and taking some away from predictive. I believe that in general, most organizations should be investing at least as much investigating into or pilot projects with predictive as with generative. And since generative gets so much of the airtime, I'm going to try to balance that airtime by focusing on predictive today. And by the way, one of the killer apps of predictive could be resolving this problem with generative. So potentially we can deliver this dream of autonomy, or at least a large part of that autonomy, by injecting a predictive model like this, a reliability model that makes a decision about which cases need human intervention. So we've got your internal human auditor here at the bottom, and now some percentage, let's say 15%, are deemed by that predictive model to be potentially wrong or problematic. And then therefore it goes over to the reviewer to get modified or filtered, right? So in that scenario, maybe we achieve 85% of the promised autonomy, right? And narrow things down to where there's only some acceptable, viable range of problematic or incorrect information, maybe along the level of what a human would do, let's say 1%. This, I believe, is the direction things are going to go. But they've barely started to. We're not seeing much of this yet. But like any other predictive use case, like the ones I've been mentioning, it still will face the same problem, which is that we're talking about probabilities and the organization as a whole struggles to get it deployed. Part of the problem is that there's no established, well-known organizational practice, playbook, paradigm for running these predictive projects so that they successfully deploy. And that's what I'm going to be introducing you today. It's called BizML. And part of the problem is that both sides kind of say, hey, it's the other person's job. So both the data scientist, the quant, the analytical expert, and their client, the stakeholder, the person in charge of the operations meant to be improved with a predictive model, both are kind of pointing to the other side and saying, these are management issues or these are technical issues. It's not my responsibility. So I'll come back to this dilemma. So I'm going to talk about the basic use case value proposition across all these use cases of predictive. And then I'll talk about a little bit more about why these things are actually failing to deploy. The technology's sound, but the organizational practice is still missing the boat. And the solution to that will be in two parts. One is a semi-technical, accessible understanding that all business stakeholders should achieve around these predictive projects, and the other is that framework, the paradigm, the playbook that I call BizML, and I'll run through its 6 steps. So when you do predictive analytics, you're kind of doing micro risk management. So this is me, I'm skiing, and I'm just a micro risk. I'm an individual case, I'm an individual healthcare consumer, insurance policy holder, and unfortunately this is the before picture. And in the after, I had ruptured my anterior cruciate ligament. I don't put this picture up here to garner your sympathy. I mean, okay, yeah, I could have like a little sympathy. But in fact, my clinical outcome was good. I can walk on my knees. That's one of the clinical outcomes without any discomfort. Very important because I've got a couple toddlers now. No, you should feel bad for my insurance company because knee surgery is very expensive. And what insurance companies do are very much analogous to or directly parallel to what predictive analytics does. Generates a predictive score, a risk level for each individual. Let's call these office workers, right? Cleaning the windows of a high rise. What is the probability for each individual of a negative outcome, right? And that applies outside of insurance as well. So Eric Webster said of State Farm, insurance is nothing but management of information. It's pooling of risk, and whoever can manipulate information the best has a significant competitive advantage. So wouldn't it be great if we could take that core value proposition, that core competency of insurance, and apply it across any industry sector? And that's what we're doing with predictive analytics. We're calculating with the model the risk of a negative outcome for each individual. That you would have spent $2 marketing to them and then they won't respond. The micro risk that this customer is going to defect or cancel their ongoing subscription. That this debtor will default or that this individual transactor will commit fraud. So in that way, what we're doing in all these predictive use cases across enterprise functions is a kind of triage, including healthcare applications, but also just general enterprise applications. Triage, prioritization. In fact, I used to get my students to stand up and get in the order of the size of their television. So everyone hold up a piece of paper, how big is your television, in the number of inches, and if it's a 0, that means you have no television. And then I ask, okay, who has a subscription to Netflix, right? And then what you see is something like this. And this is the same kind of pattern that you're going to see across all these use cases, where it's not a magic crystal ball, but we're seeing this trend, right? That you tend to have more yeses towards the top of the list than you do towards the bottom, right? So for example, for targeting marketing, if we're ordering the customers from left to right most likely to buy, according to a predictive model that was trained over data, down to least likely to buy, and if you were to contact those customers in that order, following the top curve, your profit will go up most steeply earlier on. Those upper echelons are the ones most likely to buy. If contacted, you're getting the most bang for your marketing buck. Your profit goes up most steeply, and then you kind of exhaust that diminishing returns. And in fact, in this particular example, since it's a losing campaign, if you did mass marketing on the far right, if you contacted everybody, doesn't matter what order you contact them, you're going to actually end up with a loss. So you're looking at this thing and you're saying, great, I think I know what I want to do. I want to draw the line right here at 24%, because that's where I'm going to maximize profit. But to be clear, this is the kind of thing you see with, again, with all these types of predictive use cases. You see a spectrum of options. The model doesn't tell the organization what to do. It guides how to target. Are you going to target to the top 5% most likely to be fraudulent or to buy if marketed? The top 10% of train wheels most likely to break down, therefore they should be audited. Whatever the treatment that you're targeting, right, you have to draw a line somewhere. It's called the decision threshold. And it's not preordained. So a marketing manager or other stakeholder might say, well, we don't want to do 24%. This is a new product and we want to market it. We want to get it out there as widely as possible. Maybe we should draw the line at 73% where we essentially break even, right? So for free, we can market to that many, arguably a lot better than going to the far right, mass marketing to everybody at a cost of $550,000. So it gives you these options, right? And that's how all these predictive use cases work. That's how it's deployed. More and more companies, organizations are doing this. And all of these kinds of cross-sector organizations, the way they interact with us, our experience in modern society is dictated by how we're treated and served by organizations. And more, they're making those decisions based on the prediction, the probability output by a model. And in that way, millions of decisions a day determined whom to call, mail, approve, test, diagnose, warn, investigate, incarcerate, set up on a date, and medicate. So that's how it works. They output from the model, draw a line, and decide who does or doesn't get that treatment, whether it's a medical treatment, a marketing treatment, or anything else. Let's turn to a more complete definition here of predictive analytics. So we turn to the book. I'm reading my son, Machine Learning for Babies and Toddlers. It's a real book. I highly recommend it for babies, but not for toddlers. There's a lot of problems with fuzzy definitions and such. Let's turn to this pragmatic, applied definition of machine learning, enterprise machine learning, predictive analytics. Technology that learns from experience. By experience, I mean data. Data is a long list of prior events. It's things that have happened. It encodes the collective experience of an organization from which it's possible to learn how to predict the outcome or behavior for each individual. And I mean individual in a very general sense. So it could be a human, a customer, a healthcare patient. It could be, for B2B, another organization, vehicle, image, piece of equipment. It's on that level of granularity. That's what differentiates this from forecasting. It's not the overall, how many ice cream cones are we going to sell next quarter. It's who's most likely to buy an ice cream cone. It's on the per individual level. That's the defining characteristic, and that's what makes it actionable, because those per individual predictions directly inform who gets treated. How do we make this operational decision? So each individual gets a number, and the higher the number, the higher expected chance that they will, well, whatever behavior or outcome you're predicting for that project. Click, buy, lie, or die, like in the title of my first book. Commit an act of fraud, turn out to be a bad credit risk, et cetera, et cetera. And I'm not going to inhale yet. I'm not quite done the definition, because there's one last piece that's really critical in order to drive better decisions. This is the deployment piece. This is where you actually improve business. You don't capture value until you act on it, deploy it, make a difference. Operations don't improve unless they change. We need to use those predictions, integrate them, put it into operations, operationalize it. So that's the part that's so often not achieved. So in a nutshell, the data comes in from the left, and the core method, the rocket science, the machine learning part, predictive modeling, whatever you want to call it, it learns from that, it ascertains patterns or rules or what have you from the data and generates what's called a predictive model. And that's the thing that you've gotten from the data that now is applied on a per individual basis. So now in deployment, in its use, it takes as input what you know about one individual at a time, and then it generates that predictive score, usually in the form of a probability pertaining to whatever behavior or outcome that you're trying to predict for that project. So for example, with marketing, you're looking at the customer today saying, hey, should I apply this marketing treatment? Should I include them in this marketing campaign? If I do, what are the chances there'll be a positive outcome and they'll buy our product? Now, prediction is a very audacious goal. This field has the audacity to call itself predictive AI, predictive analytics. Nobel Prize-winning physicist Niels Bohr is famous for saying, prediction's very difficult, especially it's about the future. And Jay Leno, how come you never see a headline like psychic wins lottery? Okay, totally legit question. So the way we put credibility on this field and the value propositions in general, it's super straightforward, it's real simple. You don't have to predict with high confidence in order to deliver value, like a crystal ball. Predicting better than guessing is generally more than sufficient to play the odds, tip the odds in your numbers, play the numbers game that is business, and tip the odds a bit in your favor and deliver a great improvement to the bottom line. So let's do a quick back-of-the-napkin arithmetic example for targeting marketing. Let's say you're doing mass marketing to 1 million customers, no machine learning, no targeting of any sort to start with. So if it costs $2 to contact each one and you're getting a 1% response rate, then if you get 220 back each, a 1% response rate means that after you contact all of them, you're going to get 10,000 responses. 10,000 responses times $220 is $2.2 million. If it costs $2 to contact each one, you spent $2 million to contact everyone. We get 2.2 back, so the bottom line profit is 0.2 million, $200,000. So how much better could we do by targeting? Well, let's say we took some random sample, representative sample of like 40,000, did the marketing and then waited around to find out who did or didn't respond. That's the training data, the examples from which to learn. Use that, make the golden egg predictive model, score all million customers, order them, sort them from most likely to buy down to least likely, and then draw that decision threshold at 25%. So we're going to take the top quarter, the top 250,000 most likely to buy. If the data is sound, if your modeling method did well, you might get what's called a lift of 3. So a lift of 3 means that this targeted segment has 3 times the overall response rate than the entire population. So instead of an overall 1% response rate, now we're getting 3 times that, a 3% response rate. Well, if I do the same arithmetic I did a second ago, that means the bottom line will turn out to be, and you could quickly do it on your calculator, $1.15 million. That's 5 times what we had before. So we've skyrocketed that bottom line by a factor of 5, which is such a dramatic improvement without any new marketing creative, without any new line of business or product or anything like that, just more intelligent targeting, that I hired my graphic designer who I pay by the hour, and I had him draw the star explosion thing. But hold on, this model totally stinks, right? We don't have high confidence about any individual this one will buy. It's a 3% response rate. But the value is undeniable. So we could alternatively define predictive analytics as a skunk with bling. You're not writing that down? All right. Okay. So I call this the prediction effect. A little prediction goes a long way. Predicting better than guessing, generally more than sufficient to drive value and deliver an improvement to the bottom line. And here's some more marketing examples. The improvements gained by targeting marketing with a predictive model. First Tennessee Bank lowered the direct mail cost by 20% and improved the return by a factor of 6. Target does target their marketing, improved by 15 to 20%. Premier Bank Card, a major issuer of credit cards, reduced mailing costs by $12 million. So most of what I've been talking about now is driving decision between an active and a passive treatment, right? Like Hamlet, to contact or not to contact, that is the question. But in many cases, there is no passive treatment. Like somebody asks, what's the price? Or what product would you recommend, right? Or if you're doing email, you may for the most part be emailing everybody because there's negligible cost and you need to target it. There's lots of situations like that. And in that way, optimizing the treatment of the prospect is sort of like your dating life, right? You're not in the restaurant for food. It's a sales call. You're both the director of marketing and the product, and it's imperative on you to optimize your outgoing treatment and messaging to improve the chances of a positive outcome. So how many people saw this movie Groundhog Day? Okay, most people, good, right. So Bill Murray on the left here is stuck reliving the same day over and over again. He absolutely hates it. He's stuck in his own purgatory here until he realizes that it provides for him the unprecedented superpower to try different marketing treatments on the same prospect under the same circumstances to see which leads to a positive outcome. So let's watch a 47-second clip.
You weren't in broadcasting or journalism?
Believe it or not, I studied 19th century French poetry.
What a waste of time. I mean, for someone else, that would be an incredible waste of time. It's so bold of you to choose that. It's incredible. You must be a very, very strong person. Yeah? You weren't in broadcasting or journalism, anything like that?
Believe it or not, I studied 19th century French poetry.
La fille qui j'aimerais, c'est la qu'on va faire. Et c'est bon faire un peu chaque matin.
You speak French.
Oui.
So do not try that at home. So the sad fact is we can't, right? In real life, there's no do-overs. The only recourse is to predict a priori, which is most likely to lead to a positive outcome. And the same thing applies for trying to target retention offers to retain existing customers, which is the other main marketing application of predictive analytics. So you're looking at a customer today who's, let's say, a subscriber for a magazine, and you're saying, should we issue this expensive discount meant to retain them? What are the chances that if we don't, they'll stay as an ongoing subscriber? So here's an example model within the realm of what's called churn modeling, predicting who's going to leave. This is for mortgage holders based on real data from Chase Bank. And it turns out this is the makings of a decision tree. So I'm just going to take 2 slides. I want to give you one concrete sense of what a model actually looks like. And this is just the first step of a decision tree, and it's just looking at the one main factor. Factors in this case are called independent variables, the inputs to the model, which is the interest rate. And lo and behold, it's sort of what you might expect. If there's some threshold, and if it's a higher interest rate that is above 7.9%, then you go left. No, then you go right. Okay, so if it's less than that, you go left. And that's the lower defecting group, right? So those with the lower interest rate only have a 3.8% chance of defecting within the time window, which I think was about 3 months. Otherwise, they have a much higher defection risk, right? 19%. So it's such a big difference just based on this one factor. So the machine tried all the factors, and it picked this one to start with. That's the one that makes the biggest difference. And just based on that one factor, such a big difference in risk level, in the sense, not of financial risk, but the risk of losing the customer, right? In this case, to refinancing, to go to a competing bank. So how much better could we do if we start introducing multiple factors? And in general, that's what this rocket science is for, right? It's multivariate. It considers multiple factors together about each individual to put as precise a probability or predictive score as possible. So the way you do that with a decision tree is you take both of these 2 segments and then you subsegment them again. So it's like marketing segmenting on overdrive done automatically according to your data and your particular prediction goal. It's like if-then-else statements, basically. So you grow it down. And this is about 1/3 of what turned out to be the optimal model, so I trimmed it back just so it's a little more legible. It looks arcane, but it's relatively easy to understand, to humanize compared to many of these types of predictive models. And the gist is that you start at so after training, once this model's been completely constructed automatically based on the data, then you simply use it by starting at the top, and each one of these is a yes/no question. And if the answer is yes, you go left, and if it's no, you go right, and you make your way down to an endpoint, and that's the predictive score for that individual. So decision trees are relatively simple. They're relatively easy, transparent in the sense that they're easy to understand, if maybe arcane, but they kind of consist of a bunch of business rules. Each path from the top down to an end node is a if-then rule. So this is one form of predictive model, right? There's a lot of competing forms, and generally you try multiple ones on your data set to see which does the best, including neural networks, logistic regression, ensemble models. And in general, the more sophisticated ones do better, but you lose that transparency. They become more opaque, and there's somewhat diminishing returns. So there's a lot of trade-offs, but they all function to do the same thing, which is to take an individual and score it, which is to take all the stuff you know about that individual, all the independent variables, the factors, consider them together in concert and make as precise a prediction about that one individual case as possible, so that you can sort them from most likely to least likely and draw that line. So drawing that decision threshold, that's the mechanics, right? That's the specific way that the operations get improved by way of prediction. Now, everything I've covered so far is sort of backstory. So now let's talk about the organizational dilemma about why these things don't deploy and what we can do about it so they actually not only generate value, but capture it. So again, the model takes the individual information and makes that score the probability. It's a probability. Probability is not necessarily the most exciting or accessible feeling concept in the business world, right? You could call these things basically a probability calculator. But is the world ready to embrace probabilities? Somewhat. We need to get the world a little bit further along. It's the calculating of the probability and the learning from the data how to calculate the probability that's complicated. The probability itself is not complicated. The rocket science that learns from data, that's sophisticated. But once it makes a probability, it's just a number between 0 and 1 or 0 and 100, however you want to think about it. We don't have a magic crystal ball. We have the next best thing. We're putting things on a sliding scale. What are the chances of having a positive outcome? It's an extremely valuable thing, and it's just a number. We need to embrace these numbers and actually get them integrated into operations, get them deployed. The world doesn't love probability. In Empire Strikes Back, the really smart droid, C-3PO, sir, the probability of navigating this asteroid field is 2,321 to 1 against. And our beloved hero, Han Solo, never tell me the odds, right? Now, I still love Han Solo, but dude, I'm like, thanks, George Lucas, for helping further stigmatize probability, right? Now, in contrast, Moneyball, the book and the movie, glamorized the successful union between the beauty and the geek, right? Can you guess which actor plays the data scientist in this movie? So that they actually act on the number crunching and get it deployed for the Oakland A's baseball team and proving the performance of that team much better than anybody expected given their relatively low budget. But this movie is the epitome of glossing over the math. Here's what you need to learn, real concrete, tangible, and accessible about any given predictive project. What's predicted, how well, what's done about it, right? Which is technically known to data scientists as the dependent variable, the metrics, and the deployment. So the first and third of these, what's predicted and what's done about it, that defines the use case. And you can imagine that there's so many different pairs like that. What do you predict and what's done about it? Should I, if I drill for oil here, will I get oil? That's what's predicted. What's done about it? Well, duh, right? If it's a high probability, then drill for oil, right? Are they going to buy? High probability, then contact them, right? So, is this transaction likely to be fraudulent? Then audit it or block it, right? So this isn't the rocket science part, but that concept of what's predicted and what's done about it is so general purpose, right? That's why the Harvard Business Review referred to machine learning applications as the most important general purpose technology of the century. So in that pairing, right, we need to get pretty specific. For example, for targeting marketing, will they buy if contacted? If so, then contact them, fine. Now, here's what I mean by getting into some of the details from a semi-technical basis. We can't just say, are they going to buy? That's not specific enough. You have to define a really well-defined, pertinent prediction goal, the definition of the dependent variable. So for example, okay, if we apply this marketing treatment, send them a brochure, will they, within a time window, we can't wait forever, of 13 business days, will they buy with a purchase value at least $125 after shipping and not return the product within 45 days, right? All the caveats and qualifiers that fully define what it is we're trying to predict. This is the requirements specification for the predictive modeling endeavor that the data scientists will do. And every detail matters. There could easily be 3 times as many, as I included in this example run-on sentence. But it can't be determined in a vacuum in the data scientist's cubicle. All of these factors and aspects matter pragmatically in terms of how the organization in operations is going to act on these probabilities. Probabilities of what? Well, that's what you need to answer here. So we need to get real specific. This is what I mean by semi-technical understanding. If the business stakeholders don't get involved in this level of detail and in that way get their hands dirty, their feet will get cold. That's the syndrome. By the end of the project, at the culmination, where the data scientist hands off the model and it's like, it's good to go, let's deploy it. Your operations should be improved, right? The organization's not necessarily ready for the pass. They didn't really understand exactly why we should trust the model, what the value proposition is, in terms of those mechanics of drawing that line and acting on it based on that decision threshold, that level of, and decision threshold on the probability of what? What are we predicting, right? So that level of detail, it's not the rocket science, it's how to steer the rocket. So one more aspect of this. We talked about number 1 and 3, that pair, what's predicted and what's done about it. Well, the second of these, how well, also matters, the metrics. How good is it, right? What value is it going to deliver to the organization? It turns out, and if you haven't been involved in a predictive project yet, you may not have learned this, but if you have, you probably have learned this, which is that your data scientist is going to come to you and say, I made this model, it's awesome. The precision recall and area under the curve, area under the receiver operating characteristic curve is 0.87. Isn't that awesome? And you're like, yeah, does that mean it's going to help operations? Like, how much value is it going to help? It totally means it's better than guessing. So the technical metrics are all only relative to a baseline like random guessing. And it is good to know that it's better than guessing. And that's often the most we can hope for, since it's not a magic crystal ball. But they don't tell you anything about the real straightforward business value like profit and savings. And that translation of models' technical performance into its business performance is generally omitted in these projects, which is one of the main reasons they fail to deploy. If you're not measuring the business value, you can't be pursuing business value. And that value must be estimated before deployment in addition to firmed up after deployment. So this kind of profit curve that I showed, I've been in the field for like 32 years, and I've probably only seen this type of profit curve a few times. Because profit is not the lingua franca of data scientists, who need to learn to speak the lingua franca of business in terms of those straightforward business metrics. And part of the challenge here is that you can't just look at a model and say, hey, it's worth $1 million. It depends on how you use it. The business metrics like profit and savings can only be estimated relative to its intended deployment plan, including where you're going to draw that decision threshold. So Gooder AI, which is the company I co-founded a year ago, does that, draws these profit curves, and it lets you change factors that are subject to change and uncertainty, and see how it changes the shape of the profit curve and navigate these decisions. And this is what it takes. So if any of you are working on a predictive project, we're very early stage and we're looking for early access trials. We've got about a dozen companies queued up for trials. We've got only about 4 that have actually done a trial so far. We're super early, but everyone's excited about the visibility that it gives. So I'd love to talk to you if you want to give it a spin. And here's, by the way, an article I wrote about this issue, where, look, we need to measure the performance of a model in terms of profit and savings, not only in terms of technical metrics. Okay, before I wrap up, let me actually cover the 6 steps. I sort of mentioned that the main 2 ingredients to solve this deployment problem are a semi-technical understanding and then an established business paradigm or playbook that I call BizML. Now, the first of 6 steps correspond more or less to that semi-technical understanding I've outlined today. What's predicted, how well, and what's done about it. But not quite in that order. So the first is establish the deployment goal, that pair, what's predicted and what's done about it. So what's the point? Start with the business objective, the value proposition. Number 2 is to get more specific about the definition of what you're predicting. Remember, I showed that long run-on sentence about predicting who's going to buy under just the right circumstances. And then the third is the metrics. So both the technical and business metrics, which are the ones to pertain, how are you going to measure them, and what level do they have to get to before you're going to actually authorize deployment. So these are the pre-production steps that are often omitted before you then go into actually performing the predictive analytics project from a technical standpoint. And those other 3 steps for doing the project, this is the way it's always been since the 1960s, and all the data scientists know this, when we first started using predictive models for credit scoring and targeting marketing, which is that you prepare the data, train the model over that data, and then, of course, deploy it. Now, after deployment, you need to continue monitoring moving forward. But with BizML, which is a super catchy buzzword, if I do say so myself. And the reason I spent a couple days agonizing over a 5-letter buzzword is because I want to evangelize to the world that indeed there does need to be a very specialized, particular playbook practice paradigm from an organizational standpoint in order to run these projects so that they deploy. Many business stakeholders don't realize that, let alone know the name of any particular attempt at formalizing those paradigms. So BizML is my pass at doing so. Now, the world tends to focus mostly on step 5, which is the core rocket science. That's why I got into the field. The idea of learning from data to predict, so amazing, really cool. It's the coolest science, period. Fine. But that's not where the value is delivered. It's step 6. Again, it's step 6. It's the deployment. It's where you actually change operations by way of what's been learned from step 5. But we're fetishizing step 5, both the technical and business side. That's where the hype is, as if it's intrinsically valuable, but it isn't intrinsically valuable. It's only valuable if you act on it, if you get it deployed. So here's where the 2 sides kind of point the other finger at the other side. I say, this isn't my responsibility. So the data scientists say, well, this is all management issues, right? I'm an expert. I know how to make the model. Its value is self-evident. Of course it's going to get deployed. It's a no-brainer. Whereas the business side is saying, no. Semi-technical, whoa. Probabilities. I delegate all that stuff to data scientists. That's why I have the data scientists, right? It's so ironic. In this way, the faucet and the hose fail to connect. And by fetishizing this core rocket science, it's like we're more excited about the rocket science than the launch of the rocket. That's the status quo. Now, the business professional also would protest in another way. They might often say something like, look, I don't need to look under my hood to drive my car. I don't need to know how the engine works to operate the vehicle, which is true, and that applies to me as well. But I am an expert at driving. I know the rules of the road, the way the car operates, momentum, friction, the mutual expectations of drivers, right? So I'm totally an expert. Analogously, to drive a machine learning project successfully through to deployment, you need to gain that level of semi-technical understanding of the project, right? Now I've outlined it, what's predicted how well and what's done about it today. It's not the rocket science, it's how to steer the rocket. But it's more than a 45-minute talk, right? It's a book's worth. So that's one of the main purposes of this book, my new book, the AI Playbook, which is to ramp up the business reader, in addition to the data scientist, on that level of semi-technical understanding. So they're ready to participate end-to-end, deeply collaborating across all 6 steps. That's the main missing ingredient that so often leads to failed projects. So we have to think of predictive AI not as a technology install, but a consulting gig. We need to reframe it. Instead of calling it a machine learning project, it's an operations improvement project. It's a business project that uses machine learning, right? And the solution is to make sure that the business side has upskilled on this semi-technical understanding so that then they can collaborate deeply, end-to-end across those 6 steps of BizML. That's all I got. So I think we have a couple minutes for questions. Yeah?
From the 6 steps, what's the step typically an organization spends the most time on? Is it
Oh, that's a great question. Yeah. Data. So the technical step that's heaviest is step 4, right? So, as far as the actual production steps, right? So the core rocket science, the training the model, the fun part, that tends to be using existing software. There's a lot of competing software, and there's a lot of competing methods that are embodied by those software. And there's a lot of backtracking and iteration across these steps. So I've only sort of been able to give you the overall high view of it. But in terms of the technical process, it does turn out that the prepping of the data, you need a bunch of positive and negative examples of the thing that you're trying to learn. But the data that you have now, however it's stored, wasn't necessarily stored for the purposes of this project. So there's a bunch of rejiggering. It's sort of a customized database programming task, and it does tend to always take longer than expected. But in terms of sort of non-technical steps, those pre-production steps, the first 3, can take a while as far as getting everybody on the same page and making a viable plan.
Question about the step after. This is Manny Ramos. I'm with Chief Solutions Officer at Us Digital, and I have a question about step number 6 and beyond. When we work with clients, we talk to them a lot about what happens after the deployment. In other words, the life cycle of the model after the deployment, because most of the time what happens is that they tend to think this fire and forget, as well as the teams move on. That model needs to be kept up. So I'd love to hear your thoughts on that aspect of it.
Well, it's like launching a rocket, right? So once you've launched it, NASA mission control doesn't go to bed, right? You got to keep the astronauts alive. So yes, once you do step 6, which is culmination of these 6 steps, then you're done creating a new situation, right? And now that new situation needs to be maintained, and that most notably includes monitoring the model for its performance, and its performance will ultimately degrade because you have to refresh it and train a new model over more recent training data. So yeah, there's sort of an implicit step 7, depending on how you want to frame this. Yeah.